So the first off, frequency and wavelength are related to each other, and they're inversely related. So if you have a high frequency sound, it's going to have a short wavelength. If you have a lower frequency sound, it's going to have a long wavelength. And so the frequency is the number of times it makes a complete cycle. So on this drawing, complete cycle is from the same point. So they're showing here peak to peak, for instance. But one cycle can also be valley to valley, like that. Or it can be rising midpoint to rising midpoint, or descending midpoint to descending midpoint. Okay, just be careful that if you do the midpoints, you don't do descending midpoint to ascending midpoint. That would give you only half a wavelength, right? So you got to go to the same point side to side. Now and then that wavelength is the distance from between those 2 points, and it is a physical distance. It's given for some wavelengths. It can actually be given in units that we would understand. There are radio waves, for instance. They're typically given in meters. So there's like in centimeters. So there's like a 2 meter radio band. There's like a 5 centimeter radio band. Okay, we're going into higher frequencies than that. So much shorter wavelengths in the micrometer and nanometer range. There's 2 primary types of waves we're going to be using in ultrasonic testing. Most applications. There's actually a couple more we'll talk about, but there's 2 primary ones we do. The first are what are called transverse waves. That's what's shown on the bottom here, and that's the movement of the particles, basically 90 degrees perpendicular to which way the energy is traveling. So this shows a wave on the bottom here, moving essentially from left to right, and the particle here is moving up and down to that travel. Versus a longitudinal wave, and most people think of, when they think of like a sound wave, most people are, oh, what a transverse. Most of the testing we're going to do is going to use a longitudinal wave, which is at the top there. And so the longitudinal wave is, as the wave travels, it's you can think of it like a pulse or like a pressure wave. And demonstrate that. So what I'm going to do is, it's going to be kind of hard for me to show this. So here's another picture of it, longitudinal wave. Another name for the transverse wave is also known as a shear wave. It creates shearing molecules. Also get called a shear wave. They shows how you look at. I talked about the wavelength. The example that I had was a shear wave, which is shown here. There's this gamma going from peak to peak. Other part is in the longitudinal wave. It's showing basically the point of greatest compression to the point of greatest compression. So that tells you your wavelength if you're looking at a longitudinal wave. Just kind of the definition, the book definition of it. So that longitudinal wave, this is particle motion. It's in the direction. It creates a wave front. Where the slinky led the charge. It's called the wave front. It's audible sound waves. They're longitudinal. People aren't real familiar with that pulse. It's that pressure wave. Testing, giant pressure wave moving. What you don't see is when that longitudinal wave is going up of the atmosphere, you could actually see a hump in the atmosphere. Like if there's pressure moving through waves on the ocean. Those look like, you know, a shear wave, or there's actually a pressure wave moving where that water together is pushing up. Sound waves are the same thing. So you get both those waves happening. No way, that's what. But it's going to be molecules. They're going to squeeze out at the same time. These travel fast. These are one of the fastest ways we can move material. Here are transverse waves. These go where the particle motion is perpendicular. You get they are slower moving. They lag behind the longitudinal wave, given material. Then, like I said, using angle beam tests, occurs off either side of the wave. There's one more, and this is surface wave. This is actually kind of, I said, you know, you kind of see the shear wave, you kind of see the traveling through the air. Surface wave is what the molecules very surface are doing. This creates kind of a rotary path, combination of a shear. So it penetrates to one wavelength, so it does very shallow. So we can use surface wave in order to look for surface. Example here is surface wave propagation is often used. Components that fires that travel through where we don't want to fire craft to test it. We can send the surface wave along. So it's great for surface flaws, but they are very, very difficult to generate. It takes a lot of skill. You won't see. So surface wave, I've got a little video here. What it looks like. So the properties of this are compression and rarefaction. Compression is where the density is increased. So on our, our longitudinal wave that's shown here, they're kind of showing an ultrasound sensor that's sending out a pulse right there. The compression are those areas where those lines get closer together. So we've got several areas of compression taking place. They're labeled. One's here, third one's here. There's a fourth one kind of just at the side here. So those are the areas of compression where the atoms and molecules, the material is getting pushed closer together. As you push it closer together, other areas are going to get pulled apart. Between each one of those pressure fronts, you're going to get separating, and that's where rarefaction is taking place. So, what they're showing here, rarefaction is taking place right here, here. The video link down there is basically kind of the same description I just did. So just again, you can. Amplitude, another property of waves, is the height of them, how much power is behind it. So you can see two waves here. They have the same frequency. They have the same wavelength. The one on top has a lower amplitude than the one on the bottom. And so it's that distance from essentially the center line, the average line, the wave. And so it's measured from the center portion, the center line, to either the top of the crest or the bottom of. And that, again, it's measured in a distance. It's measured meters. So wavelength is given in a distance, typically meters, although it can. And then amplitude is also going to be measured in some kind of a distance as well. Just the cycles per. Now, when we did the slinky exercise, saw it took a certain amount of time. When I sent the pulse all the way down, it bounced off David's hand and it came back to me. Or when it went down shorter, it bounced off Bria's hand. If we count that time, it can basically, and we know how fast that wave is moving, we can figure out how far it traveled. So every material is going to have a certain velocity. And even in the same material, the velocity is one of the things that it's going to depend on is the temperature. So the colder materials, warmer materials, that velocity is going to change depending on when you think it moves faster, when you think it's slower. Well, it's going to be faster. The material becomes more dense. The atoms are closer together. So the velocity travel unit of time, so we can count how long it takes to get from here to the far side of an object and back again. And if we know how fast the sound travels through that material, we can calculate how far it went. So the velocity is dependent on the frequency and the wavelength. There we go. It was muted. So this video here, this will be the last thing I'll do, and then we'll but this kind of gives you an introduction to ultrasonic